In September 2022, NASA deliberately flew a spacecraft into an asteroid at over 6 kilometers per second in humanity's first real test of whether we could deflect a dangerous object away from Earth. The test worked spectacularly. The asteroid's orbit shifted by 33 minutes, roughly 25 times more than the minimum needed to call the mission a success. There is a catch scientists have spent years trying to resolve. The shift was also about 5 times larger than the physicists and the physics of a simple impact alone predicted. Nobody fully knows why. This November, a spacecraft arrives to find out. NASA's double asteroid redirection test targeted Dimorphos, a moonlet roughly the size of Great Pyramid of Giza, orbiting a larger asteroid called Didymos. Neither object posed any actual threat to Earth. This was controlled, deliberately chosen test target. The half-ton DART spacecraft struck Dimorphos head-on, and ground-based telescopes subsequently confirmed the moonlet's orbital period around Didymos had shortened from 11 hours 55 minutes to 11 hours 22 minutes. The first time in recorded history humanity had measurably altered the motion of another celestial body on purpose. Here is where it gets genuinely interesting from an engineering standpoint. Momentum transfer from a direct impact alone should have produced a meaningfully smaller orbital shift than what was actually observed. The leading explanation involved ejecta, the plume of rock and debris blasted off Dimorphos' surface at the moment of impact, which would have added its own recoil-like momentum on top of the spacecraft's direct hit, like a rocket exhaust firing in reverse. But DART itself couldn't measure this directly. The spacecraft was destroyed on impact, and no instrument was in position to characterize Dimorphos' mass, internal structure, or the exact size and shape of the resulting crater. This is precisely why declaring the kinetic impactor technique proven after a single successful test would be premature engineering practice. However impressive the headline number looked, if outsized results depended heavily on Dimorphos' specific internal composition, it is porosity, density, and structural cohesion, then the same technique might be behaving very differently against a different asteroid with different physical properties. Exactly the situation you would face in real-time critical planetary defense scenario. A defense method needs to be realistic, reliable, predictable engineering tool, not a single fortunate data point. This is the gap the European Space Agency's Hera mission, launched in October 2024, is specifically built to close, arriving at the Didymos system in November 2026 for a planned 6-month close survey. Hera will directly measure Dimorphos' precise mass, its internal structure, and the exact dimensions of Carter DART left behind. The forensic data needed to fully explain why the impact worked as well as it did, and critically, whether that result can be reliably predicted and repeated against a different asteroid in the future. As of July 2026, Hera has already completed a critical deep space software verification 140 million kilometers from Earth, clearing its final major technical hurdle ahead of arrival. This isn't a purely academic exercise. Real near-Earth objects requiring exactly this kind of assessment continue to appear. Asteroid 2024 YR4, discovered in December 2024, briefly generated genuine concern. after initial tracking data suggested a non-trivial probability of striking the moon in 2032 and an earlier smaller probability of an Earth impact. NASA Center for Near-Earth Object Studies uses follow-up observations, including data from James Webb Space Telescope in February 2026, to substantially refine the asteroid's orbital paths, ultimately ruling out both the lunar and Earth impact scenarios entirely. The case is a useful low-strike illustration of the actual planetary defense pipeline already operating today. It's not an illusion, of course, but it looks like one at the beginning. Continuous detection, refinement of uncertainty as more data arrives, and so far every time resolution well before any deflection mission would ever need to be seriously considered. It is worth understanding the actual decision chain here, because popular culture tends to compress the whole thing into an unrealistic last-minute scramble. In reality, NASA's Center for Near-Earth Object Studies and ESA's Space Situational Awareness Program maintain continuously updated catalog of unknown near-Earth objects, tracking orbital uncertainty and impact probability for each one as new observational data arrives, typically over a period of years or decades before any object could plausibly pose a real threat. The overwhelming majority of large kilometer-class near-Earth asteroids have already been cataloged this way. The genuine gap, acknowledged directly by planetary defense scientists, is the smaller Dimorphos-sized population, up to 30,000 estimated objects in that size class. The majority not yet discovered, despite carrying enough energy to devastate a city-sized area on impact. This is precisely why validating a reliable deflection technique well in advance, rather than waiting for a genuine emergency to test one for the first time, is treated as a serious active engineering priority today. If Hera's findings confirm the kinetic impactor technique behaves predictably across different asteroid compositions, or alternatively reveal exactly how to adjust mission planning for a target with different physical properties, the practical result is a genuinely reliable, pre-validated tool sitting in humanity's planetary defense toolkit before it's ever actually needed under real-time pressure. There is the entire point of doing this methodically now on a harmless, deliberately chosen test target, rather than being forced to attempt the first ever deflection under the acute pressure of a genuine time-limited threat. There is something quietly remarkable about civilization patient enough to spend 4 years from a deliberate 2022 impact to a 2026 forensic follow-up mission, carefully verifying a defense technique against a threat that hasn't happened yet, and statistically may never happen in any of our lifetimes. It is exactly the kind of unglamorous methodical engineering discipline that rarely makes headlines right up until it's the only thing that matters. Thank you so much for your presence. Hopefully you have enjoyed this as much as I have, and I'm looking forward to your interactions. If you have any questions, feedback, reflection, I would be all ears, and I will respond to them as soon as I see them proactively. That's a promise. And make sure you're subscribed so you never miss out on any of those topics. If you'd be interested, I'm looking forward to welcome you in the next lecture. Thank you so much for your presence one more time. Del Nay.